I am an avatar created by Dr. Alemi to provide this lecture. This lecture focuses on interpretation of regression output. This is one of several videos we have organized on ordinary regression. In a previous lecture, we showed you how regression fits a line to data. Now we show you how to interpret regression outputs and test two hypotheses. First, we test the null hypothesis that the regression line does not explain any of the variation in the y variable. The second hypothesis is that the variable x does not have a significant relationship with variable y. All regressions have an embedded ANOVA. The sum of squares of the dependent variable is partitioned into two components. One sum of squared residuals explained and due to regression, and another unexplained and due to error, yielding these calculated values in degrees of freedoms. The mean sum of squares are calculated as the ratio of sum of squares and degrees of freedom. The F statistics is calculated as the ratio of the explained and unexplained mean sum of squares, and is compared to standardized distribution of F at alpha level. We will reject the hypothesis that regression is explaining none of the variance of y if the calculated F statistic is equal or is more than the value for the F statistics calculated from the standardized distribution of F at the alpha level. Regression output also includes tests of significance of the coefficients. The first line is usually the test of significance of the intercept or the constant. The first column shows the estimated unstandardized coefficient. The second column shows the standard error. The smaller the standard error, the more accurate the prediction. Standard error is the variation of y around predicted value from the estimated coefficient. The third column shows the estimate using standardized distribution, i.e., when the variable has mean of 0 and standard deviation of 1. No value is given for the intercept, as this is a constant and not a distribution. The fifth column is the t-statistic. The last column is the statistical significance, or the probability of observing the t-statistic. Here the chance of observing the t-value of 2.23 is 5%. The next line in the regression output is to test statistical significance of the coefficient for x, in our example, the SAT score. The first column shows the unstandardized coefficient that we had estimated earlier. The next column shows the standard error. The smaller the standard error, the more confidence we have in the estimate. The next column shows the standardized coefficient when the SAT scores after it is standardized to have mean of 0 and standard deviation of 1. Next is the t-statistic for the coefficient. Finally, we have the probability of observing the t-statistic. If we consider events with less than 5% chance as rare, then we fail to reject the hypothesis that SAT has a coefficient of 0. The null hypothesis is that the calculated standardized beta coefficient is 0. The alternative hypothesis is that the coefficient is not 0. We reject the hypothesis when the calculated chance of occurrence of the coefficient is less than 5%. In this case, we do not reject the hypothesis. Our test and findings were based on 4 assumptions. First is that x and y are normally distributed. Second is that the relationship between x and y is linear and not curved. Third, we assume that the variation of y at particular values of x is not proportional to x. Finally, fourth, we also assume that there is negligible error in measurement of x variable. This lecture has been focused on test of 2 hypotheses, one that focuses on goodness of fit for the entire equation, the other that focuses on relationship between x and y. Thank you for your time. Check other videos we have on fit to data, regression assumptions, and missing values.